Welcome to the video lecture series of electronic devices. This course is for the students of second year ECE, EI, IC and related branches. Here the subject code is KEC 301. Let me introduce myself. I am Dr. Sapna Katiyar, professor in ECE department at ABES Institute of Technology, Ghaziabad. Let us begin today's lecture, and today's topic is Fermi-Dirac distribution. See, this topic is very interesting. Some of the things you have to learn, some of the things you have to remember, and if required you can make a note as well. So, moving ahead, let us discuss some of the important terms. You have studied these terms in the previous lectures, but before moving further you need to revise all of these. So, first is Fermi level. What is Fermi level? See, you have studied the Fermi level. Fermi level, usually whenever you have plot the band diagram, you use a term EF. EF is nothing but the Fermi level. So, Fermi level is the energy level where probability of occupancy of an electronic state, if any, by an electron is 1/2. So, where there is a possibility of 50% occupancy of the electrons is actually defined as the Fermi level. Next is the Fermi energy. See, here we are talking about the Fermi energy. What is the Fermi energy? It is the concept of quantum mechanics, already we have discussed, which refers to the energy difference. You must remember it. This is the energy difference between the highest and lowest occupied single particle states at an absolute zero temperature. You must remember it. Fermi energy is defined as an absolute zero temperature, while Fermi level it will be different for different temperatures. So, this is about the Fermi level and Fermi energy. Next, one more important term, which is the quasi Fermi. What do you understand by this quasi Fermi energy? What is quasi Fermi energy level? It is defined as the change in the level of Fermi level as the charge carriers are added excessively to the semiconductors. You know that the semiconductors, these are of two types. It may be a N-type semiconductor, it may be a P-type semiconductor. So, depending upon the concentration or the amount of charge carriers which is going to be added to a pure semiconductor, this quasi Fermi level is being defined. So, all these three terms are important, you must remember it, but there is a relation between the Fermi level and Fermi energy. What is this? The value of Fermi level at absolute zero temperature is known as the Fermi energy. So, what is this point? At absolute zero temperature, the Fermi level and Fermi energy, both of these terms will be same. So, you remember this and note it down as well. Moving ahead, now let us discuss what is Fermi-Dirac distribution. See, Fermi level, Fermi energy and Fermi-Dirac distribution. These are the different terms. You have to define it very precisely. Don't get it confused. So, here now we are talking about the Fermi-Dirac distribution. What is this Fermi-Dirac distribution? How to define it? See, Fermi-Dirac distribution function, it is also known as a Fermi function. If the Fermi function is being written, it means that is a Fermi-Dirac distribution function. So, these are the similar names. It is also known as a Fermi function, and it provides the probability of occupancy of energy level by fermions. What is this fermions? This is the subatomic particles. So, this is how you can define what is Fermi-Dirac distribution. And electrons in the solids, see, in any solid number of electrons will exist, and these electrons obey Fermi-Dirac distribution. So, keep remember that electrons in the solids always obey Fermi-Dirac distribution. Now, there are certain considerations which are used in the development of this statistics. So, whenever you have to derive any mathematical equations, and when we are talking about the Fermi-Dirac distribution, means there are certain assumptions. What are those assumptions? There are 3 points which you have to remember. Indistinguishability of electrons, first and foremost, the very important point. Second is their wave nature, and the third is Pauli exclusion principle. As we have already discussed in the quantum mechanics, and you know that this is based on the quantum mechanics principle. So, all these 3 points you must remember it, and these are very important while defining the mathematical equation over here. So, here you must note it, the distribution of electrons over a range of allowed energy level at thermal equilibrium. So, see, each and every point is very important. Here we are talking about the thermal equilibrium. So, distribution of electrons, it can be written as what? Fe, which is equal to 1 upon 1 plus exponential E minus Ef upon kT. Here K is Boltzmann constant, K is the Boltzmann constant, T is temperature, Ef is the Fermi level, and E is the energy. E is the energy. So, all of these points, these terms you are aware with. Now, see the function here Fe. What is this function? This is the Fermi-Dirac distribution function. Fe is Fermi function or Fermi-Dirac distribution function, and it gives the probability that an available energy state at E will be occupied by an electron at the absolute temperature. Means what it gives? It gives you the value of the probability for the available energy states. And this quantity Ef, I have already told you, this quantity Ef is known as the Fermi level. So, it gives you the probability about the available states, and Ef, the term which is commonly used over here, that is the Fermi level. Now, for any energy E, when it is equal to Ef, the occupation probability, see this is you are calculating. So, here the equation was what? Equation was 1 plus exponential E minus Ef upon kT. So, when E is equal to Ef, you have substituted E, it is equal to Ef. So, now this particular term would be what? This would be 0. E raised to the power 0 is 1. So, 1 upon 1 plus 1, which is coming out as 1 by 2. So, from here you can see that it gives you the probability of occupancy of 50% means at E is equal to Ef. So, this is how you can define it for the energy level when it is equal to the Ef, which is the Fermi level, how the occupation probability is being calculated. Now, let us understand how this Fermi-Dirac distribution function, this curve is being plotted. You can see on x-axis, this is the x-axis, energy is being taken, while on y-axis, this is the y-axis, you can see f of E, Fermi-Dirac distribution function is being taken over here, and you have studied what is Fe. This term is nothing but 1 upon 1 plus E raised to the power E minus Ef upon kT. So, this is how you can define it. Now, here let us consider the two cases. See, you can see on the x-axis this energy is being taken. So, case 1, what will happen when E is greater than Ef? And the second case is case 2, when E is, this is the case when E is less than Ef. On this particular diagram, you can see Ev is the energy for the valence band, EC is what? This is the energy which is associated with the conduction band, and EF is the Fermi level. So, all of these things you have plotted, but now let us see how it vary when E is less than EF. So, what will happen over here? See, when E is less than over here, this is the greater than case. When E is greater than EF, now in this particular case, when you are calculating FE, this would be what? 1 upon 1 plus e raised to the power some positive value, because here E is greater than. So, this particular value will be what? E raised to the power some positive value, this will be the infinity. So, this is 1 upon 1 plus infinity, means you will be getting it as a 0. Second case, when E is less than EF, then here you can see what is FE? This is 1 upon 1 plus e raised to the power E is less than EF, means some negative value. This is what? E raised to the power some negative value is coming out as 0. So, 1 upon 1 plus 0 means 1. So, here you can see till the point E is less than EF, means here till this particular point when E is less than EF, because here on this particular axis E is varying. So, you can see its value is what? Its value is 1, and this is being plotted with this. And second is the case, see here we have taken this particular condition when E is greater than EF. So, when E, this energy is greater than EF, its value is coming out as what? This value is coming out as 0. So, this is the case we are considering for the temperature T is 0. So, I hope now this particular point would be clear to you. What will happen and how to calculate this function Fe and how to plot it over here. Now, you can consider two more cases. What will happen if we take temperature T is equal to T1 over here? Means now this particular temperature we are talking about. So, what will happen? See, at this particular point when you are calculating the value of Fe at T is equal to T1. So, at this particular point you can observe that some of the value, some of the energy states which are greater than EF from this particular, this is the base equation number 1. So, some of the energy states will be available after EF. Some states are available over here after this particular point. So, here you can see some of the states which are available after EF this particular point, while at the same time some of the states which will be like vacant below that particular point, and that can be observed from this curve. Means 1 minus f of E will be the available states, vacant states, free states before this particular value. So, from here you can observe that this curve is symmetrical about EF. This is the symmetrical about this particular point EF. Similarly, you can observe for the another temperature when T is equal to T2. Again, you can see some of the like available states which is being represented by this diagram. This is for the T2. At the same time below this particular point, this one, this is drawn for the T2. So, this is how you can explain about the states availability for the like filled and the vacant state, and this is how you can also understand how it is symmetrical about the Fermi level. I hope now this particular point is clear to you. Now, see what is the meaning of 1 minus Fe? This point is clear. I have already explained you, but just to recall you once, see what is Fe1? Fe1 is the probability that the energy level E1. Here Fe1 is what? E1 is the subscript. So, E1 is the energy level which is filled by an electron, and as you know that there is a symmetricity because this is filled. Now, what is the probability that the energy level will be empty? The probability is 1 minus this particular term. So, Fe1 is the probability of filled state, and what is the probability for the empty one? That is 1 minus f of E1. And the second point, E1, this is in the valence band, if we are talking in reference to the valence band. So, 1 minus f of E1 is the probability that an energy level E1 will have a hole. So, the another important point. So, this is how you can explain it. Now, from this symmetry of Fe, I have discussed, I have told you, and I have already explained you when we have drawn the curve in between energy and f of E. At that time, you have seen that the curve is symmetrical about EF. So, now when you are writing it mathematically, symmetry of Fe around EF is what? It can be easily shown f of EF plus E means after this Fermi level, if E value is being added over here. So, what is the probability for the vacant one, empty one? 1 minus this term, but here 1 minus this term, EF minus of E. See, this is when you are taking along the x-axis, plus x-axis, and along the minus x-axis. So, this is how you can represent it mathematically, this symmetricity. So, you must remember it, this particular point. Now, Fermi level in intrinsic semiconductor. As you know that you have studied all the types of semiconductors, means the classification of semiconductors on the basis of the purity. So, intrinsic semiconductors are the pure semiconductors. What do you mean by the pure semiconductors? Means the semiconductors which are made from either germanium, either silicon, group 4 materials. And in that particular case, you have observed that the symmetry, the structure is like all the bonds, the covalent bonds are completely formed. So, in that particular case, what will happen? Number of electrons will be the same as the number of holes over here. So, in the case of intrinsic semiconductor, N is equal to P, and there is an equal chance or equal probability of finding an electron at the conduction band edge, which is same as the finding a probability of hole at the valence band edge. So, both the probabilities terms will be equal in the case of the intrinsic semiconductor, and this is why. This is why, because number of electrons is equal to the number of holes over here. So, see, f of EC, which is equal to what? 1 minus f of EV. Means here you have written this term with reference to the like concentration or these available states for the electrons as well as with the holes. So, you must remember how to write it down over here. Next is EF, which is the Fermi level. It must be in the middle of the band gap for an intrinsic semiconductor. You can observe that you have studied about the intrinsic semiconductor, and there you have drawn the energy band diagram also. So, if you draw the energy band diagram, if this is the conduction band, this is the valence band. So, in this particular case, Fermi level will be in between to this conduction band and the valence band, and this gap, which is the gap between the valence band and conduction band, this is known as the band gap energy, which is represented by Eg over here. So, see, what is EI? Intrinsic level, means intrinsic level, this is an intrinsic semiconductor, it must be in the middle over here. So, and this term intrinsic Fermi level is denoted by what? It is denoted by E of I. So, see, what is E of I? This is nothing but EC minus Eg upon 2. See, Eg is the total band gap in between the valence and the conduction, and EC is the energy level for the conduction band, and this is equal to the EV plus Eg by 2. So, this is you can represent it, and Eg is what? The band gap energy. Eg is the band gap energy over here. So, this is with reference to the intrinsic semiconductor. Accordingly, we can explain it for the extrinsic semiconductor, but you have to remember some of the basic points, important points. What are the majority charge carriers? What are the minority charge carriers? which type of impurity is being added if there is a requirement to form the p-type semiconductor, which type of impurity atom is being included if there is a requirement to add the or to form the n-type semiconductor. So, now let us discuss about the Fermi levels in extrinsic semiconductor. So, in extrinsic n-type and p-type semiconductors exist. So, how to draw and how to understand the Fermi level in that particular case. See, in case of n-type semiconductor, you know that how n-type semiconductor is being formed when pentavalent impurity is being added over here. Let me write it. Pentavalent impurity is being added, then n-type semiconductor is formed. In this particular case, probability of finding an electron near the conduction band edge will be larger than the probability of finding the hole at the valence band edge. Why? Because n-type impurity, pentavalent impurity, when you are adding, each and every impurity is contributing what? Each and every impurity atom is contributing one free electron, and at the same time one donor atom. So, see, you can assume if thousands of the impurity atoms are being added over there, it means so many free electrons will be there. So, in this particular case, you can see that the probability of finding an electron will be very, very high in comparison to the hole. What will happen in the case of the p-type semiconductor? In case of p-type semiconductor, trivalent impurity atoms like boron, etc. can be added over here. So, in this case, each and every impurity atom is contributing a hole and the acceptor atom. So, here the probability of finding an electron near the conduction band edge is smaller than the probability of finding a hole at the valence band edge. So, in this case, this is smaller, while in this case it is larger. So, this is how you must remember the basics, the fundamentals, then it would be very easy for you to explain and to understand each and every point. Now, let us see, as we have discussed for n-type, you can see f of EC is what? Probability near the conduction band edge. This will be greater than 1 minus f of EV, means probability of hole near the valence band. This is the probability of electrons near the conduction band. So, this term would be definitely higher than this, and here at the same time this difference EC minus EF. What will happen in the case of n-type semiconductor? Fermi level will be close to the conduction band. So, this term EC minus EF, it will be less than EF minus EV, because Fermi level is close to the conduction band. So, the difference of EC minus EF will be definitely less than this particular term. It means EF will be greater than here EI, because EI is the intrinsic level which will be in the center itself. EI will be in the center. See, if this is EC, this is EV, EI will be in between, and in n-type Fermi level, this EF will be close to this. This is the case when we are talking about n-type. But in the case of p-type, this Fermi level will be close to the valence band. So, you can see over here, probability of finding an electron in conduction band, this is less than the probability of finding a hole in the valence band, because here the probability of holes will be high. At the same time, this difference, because here Fermi level will be close to the valence band. So, this term EC minus EF means the difference of conduction band level to the Fermi level, this will be higher than this, and here Fermi level will be below the intrinsic level, like in that particular case Fermi level will be somewhere here. So, it will be close to this particular point. So, this is how you can explain it for the extrinsic semiconductor, means for both p and n type. Now, see, as we have discussed the band gap energy, it is a constant with what? Eg is nothing but EC minus EV. I have shown you in the diagram as well. This is the band gap in between the valence and the conduction band. So, the relationship between Eg, Ei, EC, EV, EF, Eg band gap, Ei intrinsic level, EC is the conduction band for EV for the valence band, and EF is the Fermi level. So, in this particular case, if the material is n type, for intrinsic you can explain it very nicely, means it would be in the middle of the valence and the conduction band. While in case of n type semiconductor, EC minus EF means here Fermi level will be close to the conduction band because of the majority charge carriers, which are the electrons. Electrons are in the excess. So, EC minus EF, this term is equal to what? EG by 2 minus EF minus EI. It means, and here this point I have already told you, EF will be above to the intrinsic level, while in p type semiconductor Fermi level will be below the intrinsic level. Why? Because here the probability of finding an electron will be less in comparison to the hole. So, Fermi level will be close to the valence band. So, it means EF is below the, means if you are going to plot this particular line, this line will be below the EI. So, at the same time you can write EF minus EV, this term is what? This band gap EG by 2 minus this EI minus EF. This is how you can explain it for the n type and p type semiconductors, and you can represent it mathematically. And the only basic thing is, if you are able to recollect the basics, you are going to plot it in a very systematic manner. So, this is how you have to explain it. Even in this particular case, all the 3 points have been like covered very nicely. See, for the intrinsic, for extrinsic, n type, p type, and again I am telling it to you again and again. Keep remember what is n type semiconductor, what is p type semiconductor, what are the majority charge carriers in n type, where each and every like energy level is being lined over there. If you are going to plot it, how to plot it like practically. See, in this particular case, again Fermi distribution function which is applied to the semiconductors. Let us say the first case, which is for the intrinsic material. So, what happened? See, this is the case for the intrinsic material. Here you can see on the y axis the energy is being taken, while on x axis Fe, this particular term is being taken over here, and here you see it starts from 0, goes to 1, and 1 by 2 is a point, the probability of electrons which is the 50%, occupancy of electrons which is 50%, and in the case of like intrinsic semiconductors, you know that the number of electrons and holes are equal, and here the probability of finding an electron near the conduction band edge, is same as the probability of finding a hole near the valence band edge. So, here you can see this curve, this is EV, energy level for the valence band, this is the energy level for the conduction band, and this EF is the Fermi level. This level is in between the valence and the conduction band, you can see, and at the same time you can see this curve is symmetrical about this EF as well. So, this is the case of the intrinsic semiconductor. See, in the case of extrinsic, when you are talking about n type semiconductors, so in n type semiconductor Fermi level is close to the conduction band. So, you can see this distribution curve, this is close to the conduction band over here. So, this will gives you the probability of occupancy of the electrons in the conduction band. At the same time, when you are talking about p type, it means here the majority of holes will be very high in comparison to the electrons. So, here Fermi level is close to the valence band, and you can observe the behavior, this kind of behavior, this pattern is quite closer to the Fermi level, while tail is being extended towards the conduction band. This point you can see the tail is being extended towards the conduction band, and this will gives you 1 minus f of EV is what? This is the probability for the occupancy of the holes near the valence band. So, this is how you can explain it for the intrinsic material, you can explain it for extrinsic, and in extrinsic for both p type and n type semiconductors. So, I hope now it must be clear to you how to plot the Fermi-Dirac distribution curve. Thank you so much. I hope each and every point is clear to you. So, thank you so much once again.